Today we will be understanding what a Taylor polynomial is so that you can crush the AP Calculus BC questions on Taylor series and Taylor polynomials. Alright? Okay, so let's see what I have here. This is the graph of the function f of x is equal to e to the x, and it intersects the y-axis at 0, 1. Now, what is a Taylor polynomial? Right? A Taylor polynomial is basically used to approximate another function. So if I just write down something like p of x, right? This is my polynomial function that I'm going to be using to approximate f of x. So I can say this. My polynomial function is approximately going to be equal to my original function. Alright, that sounds pretty cool. So the first thing is, we're going to be centering, or we're going to approximate at 0. So we're going to create a polynomial centered at 0, whereas if I go like some point nearby it, right, nearby 0, if I approximate at 0.01, yeah, that'll be pretty close to what f of x is also equal to. So we're going to be centering, so our center is, center is going to be equal to 0. So we're going to be centering it right here. Okay, so the first thought you would think is, okay, if I'm going to be approximating it right here, the first thought is, let me try and make the point at f of 0 equal to my polynomial 0, and which should be equal to 1. And because we're making a polynomial, I'll write this. Our polynomial for the p of x is going to be equal to 1. And so what does this really mean, right? If I go ahead and graph a line, this is my line, and this line is equal to p of x, which is equal to 1. Hey, that's pretty good. That's a pretty good approximate, right? If this is my point, and I go a little far out, like 0.1, and I try to approximate it, there's a difference between the actual value in here, but as I get farther and farther out, that difference increases significantly. Same thing on the other side, it starts to increase a lot, right? But when I'm closer, it's pretty accurate. Like right here, the actual value is pretty close to 1, right? So we're pretty good. But we can do much better than this, than just creating p of x is equal to 1. I mean, it's cool, but we can create much better things. And the first thought that would come to mind is, why don't I match the first derivative here to my p of x? So you'd be like, okay, if I'm matching my first derivative term, then I better have a first degree term in my polynomial. So here we had the 0th degree term. That's because here our x was to the power of 0. So if I now make a first degree polynomial, I'm just going to use a subscript. That's going to be equal to, well, I'm going to keep this 1 here. I'm just going to say 1 plus a sub 1 times x to the power of 1. This is just, again, it's like a polynomial. It's just a coefficient that we have in front of our x to the power of 1. And so if I take the derivative of this at 0, that should be equal to the derivative of f of 0. So basically, we're trying to equal, the derivative here should be equal to f prime of 0. Well, if our function is f of x equals e to the x, if I take the derivative of this, that's equal to e to the x, because, that's one of the main reasons I even picked this function, because it's so easy to differentiate. So here is our e to the x. If I solve for f prime of 0, that's equal to e to the 0, that's equal to 1. So our p prime of 1, p sub 1 prime at 0, so our derivatives, our first derivatives match. We have p sub 1 prime of 0 needs to equal f prime of 0, and that should equal 1. So if I take this polynomial and I take that derivative, the first derivative, this constant goes away, right? So we just have a sub 1, and because of power rule, this 1 comes down and we subtract 1 on the top, so we get 1. So we get 1 times a sub 1 is to equal 1. And so if I divide by 1 on both sides, we get a sub 1 is equal to 1. So that's our first degree term's coefficient. So this term, we can just rewrite it with a 1. We just solve that. Here it's 1. So look, we just created literally a better approximation, because now not only does a point match at 0, so if I take f0, that equals 1, because here that cancels. But if I take the first derivative at that point, that equals 1 as well, which matches with the first derivative of the actual function. So now we have two characteristics that match, the actual value and the first derivative. So if I go graph it on Desmos, I can show you how much better it is in terms of approximating the actual function than the 0th degree polynomial. Let me go ahead and graph our p sub 0 of x, which is equal to, well, we first solved it for 1. So there it is. I mean, again, like I said before, I mean, it's pretty good, right? As I go to 0.2, 0.7, 0.17, yeah, it's pretty close, but it's not as good as it could be. So now we took the first derivative of it, and we got 1 plus x. That was our first degree term, and look how much better it is already, right? It's a much better fit to the actual one. Look, it's pretty dang close, even if we get a little farther apart. The other one was like terrible compared to this. This is way better, right? I would want this over the other one any day. So let's make this green. So why don't we do that with the second degree polynomial, right? Let's go try that to figure out the equation for the third degree polynomial. I'm going to go ahead and copy down our second degree polynomial, and then we're just going to have a sub 3 to represent the coefficient of the third degree polynomial. And we're going to use the same method that we used here, which is going to be, let me move down. We're just going to do the third degree term of 0 must equal the third degree of the original function at 0. So this here, again, because we're taking the derivative of this right here, right, when we take the derivative, all of these things here, right, all of this will go away, and we'll be left with this multiplied by 3 times 2 times 1. So it would look like this. We'd have 3 times 2 times 1 times a sub 3 should be equal to, well, the third derivative of this is going to be e to the 0, which is going to be equal to 1. So we have a sub 3 times 6 is equal to 1. This gives us that a sub 3 is equal to 1/6. So we can go ahead and go up and convert this into a 1/6. Okay, so let's go ahead and graph the third degree term, which was 1 plus x plus 1/2 of x squared plus 1/6 of x cubed. And let me go ahead and hide all these so that you can see it easier, but you can see that this is pretty much literally equal to e to the x. I mean, I see them, like, if I look at it close up, it looks like they're the same function. But again, as I get farther out, it does get a little bit off from the original values, but near 0, near x equals 0 right here, it is pretty darn accurate. So you can bet that if I continue to take this polynomial and continue to add and match up as many derivatives as I can write this symbolically, you know, so that it's better represented. So I'm going to say p sub n, so the nth derivative, whatever derivative we're looking at as a polynomial of f(x), right, should be equal to, let's copy down a few. 1 plus 1 to the x to the power of 1 plus 1/2 x squared plus dot 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 plus. Here's what I'm going to do, right? We have the coefficient a sub n term that we've been solving for in all of these, right? Multiplied by x to the power of n, right? 3 here because we had a 3 here, a 2 because we had a 2 here. Now, how did we solve for a sub n each time? I mean, look at this. Each time we figured out what this value was, and we had it like a sub 2 multiplied by, you would always bring down this number and its factorial. So you'd always have 2 times 1 times a sub 2 must be equal to f prime of 0. And that's similar, right? That's pretty much what we did here too. For the third degree term, we had the third degree of this must be equal to 3 times 2 times 1. So here for 3, we had 3 factorial times a sub 3 must be equal to the third derivative of x equals 0. If we had to write the actual expression for a sub n, this is the key. This is exactly what it is. This would be a sub n is equal to f's nth derivative at 0 over n factorial. Because remember, we had n factorial over here, right? And so if we just divide it, we get our a sub n term. I mean, this is basically it. So if I go ahead and replace this function here with whatever we just solved for, we have f to the power of n. So this is the nth, not f to the power, f's nth derivative at 0 over n factorial times x to the power of n. This is a nice way to write. I mean, this is approximately equal to e to the x, right? Depending on whatever degree we go to. So now, let's say now that we're just going to sum up all the infinite number of terms that we can possibly, and so we get n from 0 to infinity of f's nth derivative at 0 over n factorial multiplied by x to the power of n. This is basically what we solve for term by term. And this sum basically gives us approximately equal to e to the x on the interval of convergence. We'll go over more on that in the upcoming FRQ videos, but this is basically our series. So if you go on Google, right, and look up what's a Taylor series equation, you get from 0 to infinity. I mean, that's pretty much the same as what we had before. F to the power of n of c over n factorial multiplied by x minus c to the power of n. This is not much different. Remember, c is the center. This thing is a center, right? So here we had our center as 0, so they plugged in a 0. And similarly, this was a 0, so we just got x. There was a very important name for this. This is called the Maclaurin series because the center is at 0. I mean, it sounds like a very hard series. All that it means is that we're centered at 0. And this is a much more generalized formula, right, to say the same exact thing. I mean, these are two the same thing, so don't get confused with one formula over the other one. In the AP review sessions, they were on the YouTube channel, they were showing some wonderful equation. This is one of my favorite ones. It's the equation for a Taylor polynomial. It's basically this, right? The previous thing that we looked at. It's this, but they just rewrote it, right? They just expanded it, and this is very useful. Sometimes they would give you some weird expression like f of x is equal to, 2 cosine of 2x, and all you have to do, right, just find the center, plug it in for the first part, right, and then do the same for the second and third and fourth and how many ever you have to do. And this formula is really useful, and we're going to be using this throughout the other Calc PC review FRQs that I think I'll probably do. I really like this formula, especially for Taylor series questions. Before we end the video, I just want to give you guys one last note that you should know for Taylor series, and then we'll go ahead and end the video. So remember this P sub n series that we solved before, right? With 1 plus x squared is approximately equal to e to the x, right? If you see a pattern in this, right, that should be pretty obvious actually. This term here always turned out to be 1. Always, right? Every time, because we always had e to the 0, because each time we took derivative, it was always 1, right? So if I were to write this, it's just 1 plus x to the power of 1 plus 1/2 plus, and let me write it like this so you can see the pattern, plus 1 factorial over x squared over 2 factorial. You'll be able to see why I'm writing it like this. It's because of this. Look, when we get here, we have x to the power of n over n factorial. And you can see the connection, because each time we're starting at 0 for n, and as we go up and up, we get to this term, second term, and finally to the nth term. There's that relationship. And now, these are represented in the series, and there are 3 you should know: e to the x, sine of x, and cosine of x for the AP exam. You should memorize these by heart, and I'll show you guys the table for them really quickly right now. So let's get to that really quickly. So here is the table there. So you're going to have e to the x, which is, again, as we previously noted, this is going to be x to the power of n over n factorial, right? And again, n starts at 0 for all of these. And for sine of x, you have an alternating series with odd powers. That's how I remember this, right? And then for cosine of x, you've got, again, alternating, but you have even numbers. And these 3 you should memorize. They are pretty frequent on the AP exam. And you see a lot of patterns with them too. So that is basically it. Thank you for listening to me talk about Taylor series and Taylor polynomials. I hope to see you guys in the upcoming FRQ walkthroughs we're going to do for Calc